Hello, my name is Gabriel, and today I'll be doing a presentation on to what extent does product development improve a product. In order to address this question, we must first define what is product development. So product development is typically referring to all the stages involved in bringing a product from a concept to brainstorming to a market release and further beyond that. So here's a diagram of the product development lifecycle. So you started with research, engineering, prototyping, developing, testing, porting, sales support, all the way until you actually create a product, push it out in the market, and then solve any solutions. What defines a product? So in marketing, the business definition of a product is a object system made that's available for consumers, and it's anything that can be used to satisfy a problem. In this case, the product that I will be addressing is the 72-inch bifold table. So this report is going to be developed and created by myself to address the safety problems concerning the current design features in the 72-inch bifold table. And we will be discussing the data that was collected through both market and survey research, and all the ways that I prototyped each subsystem and tested before concluding any problems and constraints to my product. So for my survey, I surveyed 157 individuals, and 63% of them stated that they had problems with foldable tables when they were transporting them. More specifically, 73% of them stating that they have been injured in deploying those tables. So this can be concluded that there are basically flaws in the 72-inch bifold table, which is what I am addressing. So those are major concerns that will be addressed in this presentation. So how I measured how I measured these in the product is I started with research and basic research and the bifold table, the weight, the dimensions, and then any patents, because in order for me to create a product, I need to make sure that I didn't create a product that's already existing. Surveys, both market and personal, my brainstorming, my design specs based off of my brainstorming, my decision matrix, prototyping, and my test procedure. So for my market research, I found that there was yet for anybody to actually create a product that improves the 72-inch bifold table, and that competitors would already be pushing out, like Target and Walmart, pushing out the bifold tables since it's such a largely distributed product. And I figured that my main audience would be families and younger adults that would use it for events and gatherings. My survey research, after conducting all my 157 individuals in my survey, there was a big problem with the 72-inch bifold table, with the struggle of transportation and size reduction. And through my research survey, majority of the people said that they wanted a product that was cost efficient. So this led me to choosing a more accurate representation of what materials, like what plastics, if I wanted to make that wood, and all that sort of stuff to make a budget of around $100 for buying my initial prototyping products. So these are some of my survey results. I have 37% of them had problems with the hinges, 25% had problem with the table legs breaking, 35% had the tabletop plastic actually breaking, so the top of the plastic. And then a whopping 70% said that they had problems with the transportation. And then nearly 50% said that they had problems actually setting up the foldable table. So this is more survey results based on how cost efficient. So there's a range from $10 to $50. So this kind of gets a more accurate representation of how much money someone is willing to spend. And I found that the average foldable table costs around $35 to $40. So if you actually look Most people actually chose that $30 to $40 range when it came to the bifold table. So, based off of all my research and all of my results through my market and survey research, these were the top 8 design specifications that I wanted to address in my prototyping phase. So I wanted a foldable table that fits the basic 72-inch bifold constraint, have it be able to deploy in around 15 to 10 seconds. Materials of constraint be ABS plastic and aluminum legs. The table will be able to hold around 175 to 200 pounds. A table weighing less than 15. It being able to be stowed in a bag or a backpack, and it being folded in 3 sections and deployable by 1 person. These were my initial design specifications. So if you see later on, there will be some changes that I made to these in order to address a more viable solution. So through my brainstorming solutions and my design matrix, my brainstorming solutions, I selected 8 solutions that I could come up with from my initial 20 designs, and I will be using a decision matrix to kind of address all the aspects of my design and then further conclude which one of my 8 solutions I will be proceeding in when it comes to my prototyping phase. So my decision matrix shows the detailed and selected process of choosing those 8 designs and how cost, safety, other implementations, and decisions that were made in the survey will be counted. I'm going to be addressing everything on a 1 to 3 scale, 1 being poor, 2 being okay, and 3 being above average. So with stuff like ease to fold and deploy time, I multiplied the number by increments of 1 or 2 to emphasize 2 or 3 to emphasize the importance. So through my survey, the importance of transportation was very high. So I made sure that whenever I was basing that in my design matrix, that I multiplied that number to just show the importance. So here is some of my decision matrix. So you can see my initial 8 designs right there that I chose, and then you have your portability, your cost, your safety, your ease of fold, your time to deploy, durability, and such things. And then through that and the multiplication of which ones are more important, like time to deploy, manufacturing work, and probability, I selected my top 3 that I would then choose out of those top 3 to decide which one I would further pursue. So in my first design, I had a basic just bifold table, but it would be a hinge top. So it would be the 72-inch bifold table and then a secondary 72-inch bifold table that would be on a hinge that basically extends it by nearly double the length. So you would have normal foldable legs and normal tabletop bifolds, but you would just have a hinge basically attaching to them. My other design that I chose was it was kind of like a complex, almost like a W olefin hinge, as you can see. So you have your basic foldable legs, and then rather than it being a simple bifold, it actually subfolds into 6 separate sections. So with this, you have your hinges on the top and the bottom of the sides. Well, with my next design is the same sort of thing, but instead of hinges, you actually have double reverse floor bars, which extend them out forward. So after choosing all of those, after choosing the initial 20 to 8 and then the 8 to 3 and choosing my final solution, I went with the W shape as shown in this one. So this is a more polished and finalized design of how there's the 6 subsections, retracting legs, hinges that clip into each other, and top and bottom hinges on all of these sides. So after I chose my final solution, I decided to go in the prototyping phase. So prototyping is basically just the process of going from a brainstorming idea to a finalized product that can be tested in the real world and the environment. So this sample product is an original mode or form of an initial idea that serves as a basis for other processes, and it's to improve the already existing design into something that's more applicable and something that's more useful in today. So I had, in my prototype, I had different subsections to the table. So to start off, we had the tabletop. So initially, I had the idea of cutting a foldable table into 6 pieces, 3 even cuts of 12 inches. But after looking at my prototype and seeing that my legs wouldn't necessarily fit within those 3 12-inch subsections, I actually decided to change them from 3 12-inch sections to a 14-inch section to hold the legs, and then 2 11-inch sections, allowing for the design to be simplified while also fitting underneath the tabletop. Next was my table legs. So when it came to my table legs, I wanted to go with a basic cut just straight down the middle, and then I would have a retracting telescope leg, which would allow for my table to be able to be in the 12-inch resistance. But because the legs were so long and I had 6 subsection cuts rather than 2, I had to go with at least 3 section cuts for my legs. And after changing the dimensions of the table stowing system from 12 inches to 14 inches, I could change my design from a 3-part to a 2-part bungee system, which was more suitable and sturdy for deployment and allowed for a handle flip-out system, which saves a lot of time deployment and use. Next was my actual table deployment. So whenever I mean table deployment, I mean the hinges and how I basically deployed the table from a bifold to in this case, 6 subsection folds. So I initially was going to use a mechanism that would clip via the inner metal bar surrounding the outer area, but under the table. But after some prototyping, I decided to go with outer hinges on a side rail. So it would add reinforcement while also providing a structural support to my actual outside metal frame for my table. So it's basically kind of like an attic hinge system. So the hinges were made from lightweight aluminum, so I wanted to cut back on weight, and I attached them to the metal frame via metal screws and rivets. My table leg deployment. So as you can see by the 2 pictures, my table leg deployment was quite simple at first because I thought I could just easily do some telescoping legs. So on the left, that's a picture of telescoping legs. But then I decided after that posed a very complicated and annoying process to build with the limited amount of time that I had, I decided to cut the table legs into 2 pieces and almost have a bungee system that's kind of like the retractable canes. So it would conclude that the 3 padded printed pieces would attach on the outside of the middle bars, and then you'd have a bungee system running through the middle, which would clip in. So that helped. That kind of helped fold underneath the table while not having to get your hands in there. With the telescoping legs, you have to push in a pin and slide out the legs. While with the bungee system, you could just let go and it should be able to deploy on its own. And then for my table fortification, so this actually posed the biggest problem for me in my prototyping phase. I had to go through tons and tons and tons of different prototypes through CAD models and wooden blocks and frames and clips. And at first, I basically wanted to go with a CAD model piece that would snap into the bar that went down the middle of the table. But due to the middle rail, which normally would go in one direction out, it actually goes in 2 directions. So I decided to add these almost clips that would tension the 2 together and allow for my 6 different pieces to be a lot more structurally stable and a lot better for time deployment. Next is my test procedure results. So basically, initially I wanted to have a table that weighed less than 15 pounds, but after I did background information and I found that the average weight of a plastic foldable table is 30 pounds, And since I wasn't actually cutting any parts of the table off, and I was just kind of changing the already existing materials of the table, I figured out that I'm not going to be able to have my table weigh less than 15 pounds. At the most optimal level of this, I could have my table weigh 30 pounds, but it would probably weigh somewhat around 30 to 35 pounds once you add all of the things that I put on there, like hinges and frames and CAD model pieces. It would probably add a couple pounds, not saying it'd be too much, but a table weighing less than 15 pounds posed to seem a little too unrealistic, because that's nearly cutting it in half. Test procedure 2, I have a foldable table that fits within the basic 72-inch table constraint. Since I wasn't extending anything out of the table, and I was actually just changing its foldability, that was posing the most, it worked. For my test procedure 3, I wanted it to be able to be deployed by only one person in under 25 seconds. Initially it was 25, but then after seeing that it wasn't going to be as simple of a solution as I initially intended, I changed it to 45 seconds. And even with that, I still found it being somewhat unrealistic to be able to deploy this table, since there's just so many small trinkets and devices inside of it that you need to get your hands in there and undo. My test procedure 4 is to have it stowed within a 3-foot by 3-foot area. So after folding in my table and making it in the most stowed position, that was going to be useful, and it was going to be achievable. And then my test procedure 5, have the table be able to withstand 100 pounds. I initially said 175 to 200 pounds, but after doing background information, the average basic 72-inch plastic foldable table can hold up to 100 pounds. So I decided to change that to 100 pounds because I didn't want to do anything like too big, since I'm not really changing the product, I'm just improving the portability. I found that it would not be that hard to do. So in conclusion, after testing my design specifications and my test procedures, I realized that there was an importance of making the table more portable to the audience. And because of that importance to the audience, that they wanted it to be portable, I decided that it would be more practical as an engineer to prioritize the structure and the effectiveness of the portability with the cost of it not being as time efficient to set up and take down. So over the time it puts to set up the table, because of me prioritizing the structure, I was able to withhold the force, but I was compromising the 45-second deploy time. And in final conclusion, the product posed a ton of problems during the prototyping phase because of the process, due to all of the small trinkets needing a little bit more, better machinery, like having manufacturers specifically make pieces out of aluminum and metal, while we were only given the resources to make these CAD models through 3D printing. And with these resources, I feel like it would create a product with a complex, efficient solution for some. But I found myself supplying the subsystems due to the lack of time, so I compromised some of the subsystems and kind of pushed subsystems aside because of the lack of time. And that was it.
Oh,